Hello everyone.
So,
Hope everybody is doing fit and fine during this period of COVID. I'm sure everybody's just excited to know more about computational design. Before we begin with the presentation, I would like to just share a little bit of background about myself. I graduated from Hindustan University in the year 2015, with Bachelor's of Architecture. And then after that, I worked in Chennai for a year or so. And then I went to the United States, did my master's in advanced architecture in the University of Illinois at Urbana-Champaign. And after graduating with my master's degree, I started working in the US for a year or so. And with those experience, I came back to Chennai. Now I'm looking further what next to be done in architecture realm. So overall, I am pretty well versed with a lot of different softwares, I would say. So today we are going to learn about a software or a technology which we are going to implement in architecture itself. I will quickly share my screen. I'll start with presentation.
participants can have your mic on mute.
Yeah. Tanya, can you see the presentation?
Yes, we can see.
Okay, okay, got it. So today the topic for the presentation is computational design. I'm sure everybody would have Googled about it or heard about it somewhere or some at some point, since everybody is doing a lot of technology-based architecture these days. So I think the images itself speaks for itself. Like on the left-hand side of on the first screen is the robotic arm, which uses a lot of technology-based language, like computational language, to do a model or to do a 3D model or anything of that sort. And on the right image, it shows like different iterations a computational model can play when you want to present something to a client, like multiple options it plays, so that you can give like maybe 10 or more options in a short period of span to the client, so that the client gets more visualized about the project, what he's going through. Moving on, if you do like a Google search on computational design, definitely you're going to see a lot of parametrical or a lot of wavy shapes or a lot of different kinds of forms, which definitely doesn't follow function. You can see like that, or maybe you can say like these forms can follow function at some point. So basically, how form follows function. We've heard this sentence multiple times. So computational design wants to make the form very irregular or weird, so that human mind can use the language of computational design and how that language can built into a functional form on the real world. How it started was back in 1940s. We were all aware with how computer can help us design. Like we use different softwares, like in an initial stage, how computer can, or obviously we use a lot of drafting during those days, and slowly we moved into computer and how it helped us design. But in today's world, we are just trying to experiment with how computer can get involved into the design process itself. So that is a big leap with how it was and how it is now. So maybe like the shifting rules, I would say it depends. Like in 1960s, designers used to draw on a blueprint, so that they can just present it to the client or to the people who are contractors who are working at the site and understand the drawing. Like everything was hand sketch. It was very difficult, obviously, but even those days, buildings were built. And then in 2000, designers uses computers to draw the blueprint via computer softwares like AutoCAD, which was like the basic one which everybody got to know. And then in after like in 2030, we are expecting the computer itself will start printing like a 3D model, or more advanced in a way how architecture is going to be. uh, Before learning what computational design is, let's learn what is not a computational design. Obviously, everybody would have heard a lot of terms like ArchiCAD or CAD or building information model, or all those kind of digital design or those kind of terms. But all these terms are not linked with computational design. We'll just move on with each term. So computer aided design. So nearer digital replication of an analog technique. So we're using CAD in these days, and also we've jumped and shifted into a lot of other softwares. But before it was just CAD, and then where CAD started, we are just using analog technique, like we're doing sketching on the paper and then putting it on the software, so that we can move on with how a 2D element can look, and then later on play with the 3D element in AutoCAD. Building information model. When it comes to building information model, it is always like we are just trying to give a symbolic digital simulation of all the building elements. Like BIM is a platform where Revit acts as a main software. In Revit, a lot of different criterias of architecture gets involved, like architect, interior designer, contractor, civil engineers, structural designers, electrical, plumbing. All these layouts can work on Revit, and then all those drawings can be accessed by all the different platforms, so that everybody gets the access of the whole model at one go from anywhere in the world. That's basically BIM, the building information modeling, which is again not a computational design. Moving on to the digital design. Digital design is a different whole concept which is mainly used by gamers and graphic designers. So it's a broad topic, I would say, on a different level. Moving on to 3D scanning, obviously in the latest iPad, we've seen that Apple had put a scanner in the camera, as in next to the camera itself on the iPad, where we can just scan the whole space or a building or whatever it is, and then take that material into a 3D model software like Revit or SketchUp or Rhino, and then start modeling. So that is a different software where we're using a lot of point cloud data, where data plays a major role in putting that into the computational design. But again, this is not a computational design. Moving on to, now we've learned what computational design was not. Now we'll just try and understand what is computational design. So when it comes to computational design, it is definitely very difficult to make anyone understand, because all the different architects or designers or any world realm architects have different concepts and different theories on computational design. So the basic idea about that is computational design is the application of computational strategies to the design process. So as a lay architect or designer, what we generally use is we use our intuitions or experience we've got in the past, and then try to incorporate that into software and come out with a plan or a design or a model or anything. But computational design can help you spit out a lot of different options for the client, so that the client understands there are a lot of different options he can play with, and whatever he likes or whatever the design has spitted out as a result, that can be played. So computational design is a process in the whole to gain the ultimate result with multiple options, like thousands of options, I would say. Um, let's move on to the terms which are dealt under computational design. Obviously, everyone would have heard about parametric design. So parametric design is basically using a lot of parameters. So in Revit, we are using parameters. We give parameters as commands, and then how a building or a form or a structure or a column or a material is used to make the Revit model very user-friendly, very detail-oriented, very understandable, so that everybody understands the drawing. So that way, a parametric design comes into play, where we are just trying to put in a lot of parameters into the software, and then it generates lots of ideas and different concepts. Moving on to the algorithm design. So in algorithm design, so I'm sure everybody is aware of the game Fortnite. So in Fortnite, what happens is all the players are put into one like an island, where 1,000 iterations of with a given particular dimension and given particular way of method we are playing with the Lego block. So that's how you can give your command to the software or to the platform, and then that platform helps you understand by making different concept, different iterations, a lot of multiple iterations. So all these terms are always interconnected with each other. And next is generative design, where the generative design is multiplying the plan into different concepts. So that is the main idea of generative design. This is again like interlinked with computational design itself. The other one is evolutionary optimization. So basically in this, what happens is you're trying to understand the building in and out, the form, the structure, everything. Computational analysis. So before the building is getting built at the real world, on the real world, what we need to do is we have to understand the thermal capacity of the building, how the structure is going to be, what the foundation is going to be. So before it even it gets started built, we have to analyze everything in the software itself. Obviously, the software won't give you like the exact result of the real world, but it is the process where it takes you, so that you can save a lot of time, a lot of efforts, a lot of money as well. So that is very helpful in computational design. The other one is form finding, where the material itself is used so that it finds the form. With the help of different materials, we can use different way of how the form can evolve. So here, like right now, the form is getting built in a very different manner, whereas on this part where we are trying to show how the form is using different materials, like this is using a block, and then the next one is using like a fabric material or anything. It is just playing with iterations. The next one is machine learning, which is very new to computational design. Obviously, machine learning, artificial intelligence is all playing a big role in all the fields, not only in architecture. So that is definitely playing a big role in computational design itself. The other one, the final one is self-organization, where once you put in the commands, like put in the computational language in the software, it tries to bring in different methods and different platforms and different concepts, so that you can have multiple options and variety. So you can provide it to the client, to the business people, or whomsoever you're showing it the project as. So basically, a computational design plays with all these terms, and everything is interlinked, and everything plays a big role in bringing out multiple options. And once you see the options, it is definitely known that can never be done by just a basic software. You need big software, and you, after seeing the results, you'll always be astonished that how a computer spit it out like a big, different design, weird design, which is going to be a masterpiece, I would say. So moving on, where we can see the logic of the human brain and how the geometry he wants to achieve at the end. But before achieving the geometry itself, they are playing a role in the middle as computational design, as a plugin, as a big plugin. So by using that particular platform, we can have multiple iterations. And the tools mainly used were generative components, which is way too old, and Grasshopper, which was just introduced in the year 2003 or so, and then it came into like proper booming stage in architecture was in the year 2014, where it became popular and everybody started using Grasshopper majorly to show different iterations, to do a lot of parametric design, to do a lot of, so it's basically using a lot of computational language, where you have to play with if, or, but, and true or false, all these kind of parameters. You have to give it to the computational language, and then you can have your own repetitive model. You will never get tired of doing repetitive terms, as it is very fast and very user friendly once you know how to use Grasshopper, which is really popular and which is really important to for all the architects to learn this software. The other one is Dynamo, which is a big plugin with Revit. It is again similar with Grasshopper, but a little different orientation of with graphs and computation language we're using. Like it is not every computational language is not coding. It is not equal to coding. It is basically using different language where we are trying to incorporate with if, but, and or, which is obviously used in coding language, but it is a different platform. The other one is Marinette, which is just invented or incorporated, where it is slowly growing up. So the main major I would say is Grasshopper. I'm sure everybody is well aware about that. And how computational design allows design to be more innovative, insightful, and also personalized. So all these things is what architect is willing or wanting to show to the client. Obviously, he wants the design to be innovative, insightful, and personalized as well. So by using computational design platform, we can have multiple iterations and play around with that, and which is very fast and very easy generation. How computational design works. So first you have to give a shape, like a constraint on the shape where what kind of dimension you want to give. After giving that, moving on to the next step, it optimizes. Like you can give the optimization by putting up the dimensions, the thickness, the how strong, what is the strength of the material, etc. Everything. After that, you just the software generates a lot of different iterations, and then you can rectify those iterations, and then once the result is produced, you will definitely be shocked by looking at it, by the way it is produced, like as it is trying to show very way too advanced type of form, where you're definitely shocked to look at it, and you will be sure that humans cannot create this. So a software, once a software creates it, a different platform is used to bring it into the real world. I'll talk about that platform as well in the further slides. Um, the famous architect Bjarke Ingels group, BIG, everybody would have heard about it. So they took part in the competition and won this competition proposal. The site location for this is Kazakhstan, where they are trying to build a national library. So the concept of library is like a loop. We can call it as a Mobius strip. So if you Google Mobius strip, you will understand what is like. It is a proper loop which has only one surface, and that's the concept they wanted to incorporate. And that's when they try to use a lot of Grasshopper, a lot of Rhino, and a lot of other platforms to bring it into functional platform and show how a Mobius strip from a very utopian world can be put into the real world. So this is really surprising, and the way how the structure is built and everything is being showcased, and how they try to come up with functional space with the design itself. What does a designer need to be successful in computational era? I would say, like, the first, he needs to evaluate the competency. Like, he needs to understand what is the method and how it is going to be, and what kind of steps we are going to take to achieve the form. So before, like, after brainstorming, we have to know, understand the steps. So in this GIF, you can see a person is getting stuck in the machine, in the coil itself. So he tries to learn how he's trying to evaluate the competency in that loop itself. And the next one is understanding the design. So whatever the design proposal we are giving, we first have to understand it in the Rhino or Grasshopper model itself. So by understanding that, one can understand how the technology is going to work and how it is going to be brought into the real world. And the next one is, we have to think very critically while playing with these softwares. But once you're truly well versed with Rhino and Grasshopper, you can just be a king of those designs. Since when you started, you obviously have learned CAD and then moved into all the advanced softwares. So as you became advanced in those softwares, you can also definitely become advanced in this as well. So where that is where we have to think critically, and also we have to keep how the market is going on with the technology, how we are going to incorporate these designs into the market itself, how it is going to play a major role in the market. And on the whole, we have to actively learn artificial intelligence, which is majorly very important in today's world, where everybody is learning AI, and in every platform we are using AI. AI has become like the real time, and it's going to be the future in coming years. 5 ways computational design will change the way you work. So first, let's explore multiple design options. As I was mentioning earlier, you can have multiple design options where you can play with the building's form, the building structure. It is not only playing with the form, it is always playing with how the building is going to be functional in a short period of span, where obviously architect has to meet the deadline. So say we are designing a toilet. Obviously, toilet designs are really boring these days. So once you put in your form's requirement, the client's requirement into the Rhino software and Grasshopper plugin, it can iterate a lot of different toilet options so that it is functional with the client itself. So Once that is done, that is just moved apart, and then you can focus on major things in a big structure. Like you can focus on other interesting things than just sitting on a toilet layout. Moving on to the next one, this is a major leap between Excel and other softwares, because always all the data we are trying to put, like the bill of quantity, the door schedule, the window schedule, the area statement, everything we are trying to incorporate into Excel sheet. So what happens here is Dynamo, which is a platform in Revit. It has different platforms in like graphical based or like a Dynamo language itself, where we are trying to put in the data of the plan or of the design into the Dynamo, and then from there we are just trying to export it into Excel. And once we want to do any changes in Excel or iterate it, we can again import that into Dynamo. So that's how Dynamo and Excel plays a major role. But Excel, it can help you just type in the details, but Dynamo can help you bring in all the details at once in very quick format, in a very easy way. So that is easier to export and import. It is vice versa. And how an automotive steps are done in Revit, which is done in a Grasshopper, which is very easy and very fast. So by just incorporating the size, the number of dimensions, the number of sides, the number of shapes you want to create, like what kind of shape you want to achieve, you can do multiple iterations on a repetitive mode. So by doing that, it is very easy and quick, and you will never get bored of doing repetitive things. As in AutoCAD or Revit, you want to do repetitive things, but it is very tedious at some time. But here in Grasshopper, you just have to plug in and move the slider left to right, so that you can give different dimension and different shape iterations. Next is testing what your design is really going to do. Obviously, we are going to test it before going to build it, and then by using the computational softwares, we can definitely test. Computational design tools gives you a way to make this determination as the design progress, not just at the end of the process. So it is not going to achieve the end process in the real time, but it is going to help you with the process and bring in the result which is closest. And the final one is thinking algorithmically. So obviously, algorithm is a play where we are trying to understand the process that can understand and that can be understood and being repeated. So by doing algorithm process, like as I mentioned earlier, these algorithms can help you give different iterations itself. Right? So right now you can see there are multiple iterations going on in this particular site area, where we are having 3 buildings, or sometimes we're having 5 buildings. We're just trying to show different options in a quick format. Next, the main platform, like the main application. So computational design is the best application for 3D printing. So obviously 3D printing is the most user-friendly, most easiest and most quickest way, where we want to bring in like a quick small model or iteration. We want to show it to, we want to present it to the client or anyone in real time. And it can also generate multiple varieties of different shapes, sizes, and also complicated shapes, you can say. So I would just give you a small case study on that. So this is the illuminated 3D printed installation, which was installed in Singapore by two different professors from Singapore University and of technology and design, where they are trying to incorporate Grasshopper, and they are trying to use materials which are like nylon and ABS. These materials were mainly used to bring in this structure, and this structure is always also interactive. When humans move under it, the lights blink according to it. So that is because of all the sensors they have attached to this particular structure. So it predicts static performance on the installation, and the dimension for this is pretty big. It's 10 meter by 6 meter by 3 meters. It contains 152 nodes that are 3D printed using ABS and nylon to contain internal custom LED bulbs. So this structure is an installation for one of the events organized in Singapore every year. I would like to show you a small video of how they made the process itself.
We are always looking at nature as a source of inspiration. And in this project, we were thinking about the way our brains work, how ideas are created, how neurons talk to each other to create complex thoughts. We look at that idea from science and we try to create into a structure, something that we can show and represent this miniature world in a large scale.
Nature is a topic that could be taken from many different sides. Our idea of using a natural network combined with light, I think, is bringing the concept to a more experiential level in which the structure is going to react with people and it's going to create a really interactive experience.
I hope we can actually approach to a broader range of ages, not just like people so interested in technology and modern design, but also like older people or younger people.
So this is the idea of how they wanted to use the software and different technologies to bring in using the major application, which is 3D printing, and showing the iterated structure so that everybody can just enjoy the view or whatever it is in the installation.
We are always looking.
The next one is 3D printed grotto, it is called as. So it is a 7 tons complex ornamented structure that was 3D printed using sandstone material. So in this structure, they used multiple different variations, iterations, multiple complicated shapes. They wanted to show it in a museum platform where people can just come, look at it, admire it. It is a major one. It is pretty big, and definitely it is complicated to do it in a basic software. So that's when computational design comes into play, and where we are trying to bring in this structure and showcase it to the world so that they can understand that these designs can really be built in real time. And also, just to iterate it, we can use 3D printed software, 3D printers. So entirely designed by algorithms and optimized to generate differentiated surfaces, porous and various types of geometries. So they use multiple geometries as well. And I would just show a small snippet on that. So since you saw in the video, there was like a lot of detailing involved, a lot of joints, a lot of way too advanced way of designing is involved. So all these can be done easily with the help of computational design. And the other industries where computational design is using 3D printers is robotic industry, medical industry, fashion industry, and structural industry. So in robotic industries, people are trying to build a lot of robotic forms. They get destroyed. They have to build it, rebuild it again. So 3D machines are very handy to make it quick so that they can play with small iterations at like multiple times in a day itself. It takes a lot of time to rebuild it with by hand. So 3D printers come into play. And in medical industry, where we are using prosthetics a lot, where we're just trying to build in different arms or legs or whatever it is required for medicinal help. So that's when 3D printer again comes into a big play, and different materials can be used with computational design. In fashion industry, people are just trying to showcase their different way of how clothes can be worn, or what kind of materials, different materials can they use other than fabric itself. Like how can they take fabric into the next level? So that's when this comes into computational design and 3D printers comes into play. Structural industry is just playing with experimental structures, where so this one is a small structure done by Zaha Hadid itself, where the architecture's firm wanted to try and show how 3D printer can work in a very a parametric manner, in a very wavy form. Obviously, Zaha Hadid's designs are all wavy and all out of the box. So they wanted to try out, experiment it. So that's why they wanted to bring in 3D printers into play. And then this is like a small, this is a studio, a semester in which is done in Cornell University every year or so, or maybe every alternative semesters they might have. So they mainly deal with computational design and what they are trying to show with computational design and how iterations can be achieved. So I would just play the video.
So typically we start the studio with what I call abstract models. The students started with plastic cups, paper plates, rubber bands, and zip ties. And then the students had to develop their own algorithm.
And it really was a challenge having something that you see and interact with every day and trying to find a different way to see it, a different view. And that's really what this studio is about, taking something that's ordinary and making it extraordinary or unusual. We use the technique of curved folding, which is curves on a flat surface to create a 3D surface. From the sketch, we began to figure out what the angles would be, what the shapes would be. We began to then test out ideas in small models, after which we were able to move to the computer and make our investigations even more clear.
So as you can see, they're trying to explain, they're using physical models, iterations, they're using a lot of grasshopper repetitive graphs, repetitive language. So it is very being user-friendly and very seamless when you use these softwares of computational design.
So typically,
and moving on to the case study, this is the hospital building, which is in Mexico. So this building, they mainly used a lot of computational iterations, a lot of grasshopper and rhino model. So the hospital's name is Manuel G. Gonzalez Hospital in Mexico, where initially how the architects started making the iteration is by just hand sketching, which obviously everybody is doing these days, just brainstorming their ideas. So after that process, they are trying to take that idea into Rhino model and Grasshopper, and then they are trying to plug in with how this shape can come into real time. First, they are just playing with rectangle and point manipulation. They are just manipulating those points with rectangle as the base. So that is the iteration they are trying to incorporate. And after that, they are trying to get in the outline mesh plus Weavebird. So Weavebird is like a plugin for Grasshopper itself. It's like a small input given to the Grasshopper software. So where you can literally weave the structure in Rhino model. And after that is done, a perspective is generated. So these are all the basic iterations done on the software. And then once they have achieved that, they move on to the real time, where they're trying to show how the structure is built, or what the structure is, or what kind of materials they are going to use. So this structure is mainly done by two designers from Berlin, and the location of the site is Mexico, where they claim that this structure, by putting it in the facade of the building, it reduces the pollution produced by around 1,000 vehicles per day, and the area of the whole structure itself is 2,500 square meter, and each block is made up of 5 three-dimensional modules. So each module is separate, and then how they join, that is we're going to see in next slide. So this is the joinery detail, and how it is getting attached to the facade itself is being shown here. And material used for the structure is fire-based ABS plastic shell. So these are all fire-based ABS plastic shell with steel fixings. So they have steel fixings on the facade and on to join those blocks in itself. And then the coating for the material is titanium dioxide, is the coating pigment for the structure, the color which gives. And the maintenance for this structure is pretty simple. You just have to spray it for, like, say, between after 5 years or 5 or 7 years. So it has the guarantee of 5 or 7 years for the pigment, and it takes in the UV ray, and it doesn't reflect it inside the building. So that is a good absorption material. It has capacity, and how it is installed is they are using a mold, a steel mold, where they are trying to bring in the material, the material which we're talking about, ABS plastic shell, and then they are trying to incorporate with the shell as the basic, and then they are bringing the shape. And by doing these different form, they are trying to minimize the radiation of the sun, so it hits into different layers and it just reflects back. It doesn't get inside the building, or it doesn't get absorbed by the material itself. and then this is like the installation they are doing with the steel, and then this is again a different installation. This is the joinery detail. This is the joinery detail from back to back. I'll just play a small video about it.
A striking building on the Mexico City skyline, this hospital tower also has a very unique feature. It eats smog.
This facade is coated in a special material, which, when hit by sunlight's UV rays, begins to break down pollutants. Designers say it neutralizes the effects of 1,000 cars every day.
The genesis of the design began some 10,000 kilometers away in Berlin.
We were witnessing the rise of smart materials and their applicability in architecture. And what we saw was a city full of built structures that were essentially dormant.
Using material called titanium dioxide, they developed a pigment that coats the tiles, or so-called nodules. When pollutants come into contact with metals, they turn into compounds like water, carbon dioxide.
The design is inspired by natural shapes. It's kind of similar in appearance to corals. There's a need in the photocatalytic reaction for a maximum surface area. And the natural forms of corals, for example, is very good at doing that.
So the main concept used behind this design is the concept as sponge or corals or honey. It looks like honeycomb as well. That's what the designers had to say. So that's the concept adapted by Mother Nature itself. So how architecture is getting involved into, like how architecture is adapting, obviously a lot of other designs also are also adapted. So how in today's world we are trying to bring in Mother Nature into architecture is really interesting with computational design. So that is taking into the next level, I would say. And moving on to the final part. So by computational design, we have more questions than what we have learned. Like we have more questions than answers itself. So what kind of value will you give to the companies when they start doing designs? Will you value the company better, or will you value the professionals, or will you value the people who are knowing the softwares, or what kind of value we're going to give for the design companies who are going to use this technology itself? And then what kind of new roles or opportunities the company can generate by incorporating computational design as a main platform? And then will artificial intelligence take the craft out of design? So we have to keep that also in mind. Obviously, we are not, we are trying to use our brain, and then we are trying to give in our language to the software so that it generates the model according to whatever is the thought process involved. So even that is a big concern. And what kind of new products or revenue channel for the business, like how this is going to generate new materials, or how this is going to generate new products in the market, or what the market level is going to be with respect to what different softwares we'll be using, and how the company is going to run. All these questions are definitely in the mind and are all in the process. So as I've said earlier, computational design is more like computing a language to reach the process, and it is mainly done with a lot of iterations and bringing different multiple results. So it is basically doing a lot of iterations, keep on doing playing with the softwares. So that is the ultimate goal of computational design, where it can spit out multiple options to produce it to the world. These are the references which I used for making the presentation. And then, does anyone has any questions on computational design?
Students, if you have any questions, you can raise your hand, or you can even type it in the chat box. If you have any questions related to software, because architect Dikshit here is skilled in all the latest softwares. You name it, he will know it. Rhino, Grasshopper, Lumion, then Enscape, Twinmotion, Spark. So anything at all. If you have any doubts in general ideas about softwares, knowledge on softwares, you can discuss with our guest here today.
And before that, I would like to thank Hindustan University for giving me this opportunity to present in front of multiple different students. And I would like to thank Ms. Tanya and Mr. Kalyan to help me coordinate with the presentation. So this is, and also I would like to thank our head of the department, Ms. Shiva Chandar, to give me this opportunity again.
Hi, I'm Kasi Rajan. Can you hear me?
Yeah, I can hear you.
SRM here, assistant professor. Okay, well, the question is, I mean, it's very interesting. First of all, thanks for the presentation. It's very wonderful. By the way, I'm handling the subject for this semester on architecture of the future, where we are dealing with computational design. So thanks, and it was timely. I just want to basically check with students, and I don't have any questions per se, but I just want to have one clarification from you. So now that Dynamo is like picking up and Marriott is like on in the, how was Dynamo standalone software can be of any use to architects as of now? Because in I mean together with Grasshopper or Rhino, Dynamo is a very wonderful tool, but how individually as a standalone tool it could help anyone, because that's the only open source that's available. That's what I think.
So Dynamo mainly plays with Revit, and in Revit, obviously, you do a lot of planning, structural, lot of detailing, a lot of detailed drawings, sections, elevations, and everything. So by just and once you're done with all those drawings, you have to do a lot of labeling. You have to dimension that when you produce those drawings to the vendors, to the contractors, or to anyone else who wants to understand the drawing, you have to use Dynamo as a platform. It is just that you have to give in your plugin to the Dynamo. So I've always used Dynamo with Revit. So while using that, it is very user friendly to spit out like an Excel sheet itself, like where you're doing door schedule, window schedule, where you're doing dimensioning for the model, where you're doing different export and import into Excel back and forth, and where you're doing bill of quantity, and also where you're doing the area generation for the whole building. So Dynamo plays a major role in that. So by using Dynamo with Revit, it is very user friendly. But as a standalone, I'm not sure about that, because I've always used Dynamo as in Revit itself.
Okay. Thanks. Okay. Students, 9th semester students who are undergoing architecture of the future, please post questions if you have. I mean, everyone for that matter, but specifically, we have dealt with some things, but I mean, most of the thing was mentioned out here. Dikshit has mentioned it.
Sir.
Yeah.
So this is Clarence from second year.
Yeah. Hi, Clarence.
Yes, sir. So right now we are on the stage like we are moving on to the software. So there's a lot of variety of softwares like SketchUp and Revit, right, sir? So out of your experience, which would be the best one for us to learn?
Actually, I'm not able to hear your question. There was a lot of disturbance. Can you please frame your question again?
So we are just pursuing second year right now, sir.
Yeah.
So we are in a stage like we are going to move on to the software things.
Okay.
So out of your experience, which software would you suggest for us to learn, sir? Well, like which is the best one for us? There's a lot of softwares like SketchUp and Revit and all.
Yes,
So which
definitely.
one would be your best pick?
Firstly, I would like to know what softwares you know personally.
I know about SketchUp, sir. It's for 3D modeling and rendering.
Yeah.
AutoCAD is for 2D and Revit is for 3D.
Got it. Are you well versed with all the three softwares?
I'm not like completely professional in it, but just a basic knowledge of it, sir.
Okay. So firstly, obviously you're well versed. I think you're obviously well versed with all three softwares you mentioned. So learning these three in detail would be really helpful as you keep on furthering with your career. These three softwares are basic, obviously, but if you keep learning Rhino and Grasshopper as well, that'll really help you with studio design, as in your semester studios, where they'll give you different projects each semester. Obviously, you can bring in different iterations and different options, so that by using those, as I mentioned in the presentation, by using Grasshopper as a platform, you can use Rhino. Rhino is similar to SketchUp but little advanced. So Rhino, you can use that, and then you can use plugin as a Grasshopper. And by learning Rhino and Grasshopper, you can really excel. And by doing like conceptual design or in your schematic stage, you can play with multiple options and you can show it to the juror so that he can understand like how these different iterations can help in the design process. Or if you directly start using AutoCAD or SketchUp or Revit, you'll be accustomed with one particular concept itself or one particular plan itself. But by using Rhino and Grasshopper, you can play with multiple options. You can give different iterations. So that is the only word which comes to my mind. When you use Rhino and Grasshopper, you can have multiple iterations, multiple options. You can produce it and you can show it to the juror or your faculty or your professor, or in real world you can show it to the client. Obviously Rhino generates like way too advanced style of design, and that's what it's expected out of students when they are in the university, when they are studying. But in real time, Rhino is definitely used so that they can have a functional, very functional way of design, and which can be brought into the real world. So that is, I would say, I would suggest you to learn Rhino and Grasshopper.
Fine, sir. Thank you.
Yes, sure.
I think I have one small clarification to check with Dikshit and Kasi Rajan
Sure.
again. Yeah.
Sure, sir.
Yeah. One is like now, I mean, when you are in presenting, you said think algorithmically. I mean, what do you mean by that? Can you slightly elaborate on I mean, how to make the students think algorithmically? Can you explain on that bit?
So algorithm meaning when you put a point, say in AutoCAD itself. In AutoCAD, there's a command as algorithm, and where you can just play with a dot. When you put a dot, you need multiple different shape of that particular shape. Say you put a dot, or you put a square, or you put a circle, or anything. And then when you give the command algorithm, and then when you just hit enter, it gives you different shape or different multiple circle or multiple, making it a big form. So that's when you're trying to think your design into an algorithm way. When you try to make a design, like when you try to make a structure, or when you try to make a different out of the box planning or anything, you have to play with algorithms so that you understand if you have this room here, or when you have the room here, or when you have the room facing the other way, how it is going to work with respect to the sunlight, the climate, the weather, everything we have to keep in mind, and everything is going to take place back and forth. So it is going to be a vice versa thinking when you're playing algorithmically.
Okay.
Does that answer your question, sir?
Yeah, I think it's. I mean, I'm kind of understanding. I just want the class students to be clarified with that particular point. Yeah, thanks.
Sure. Sure. Thank you, sir.
There's someone who's raising the hand, Akshita.
Yes, sir. Hi, it's Akshita here.
Yeah.
Hello, hi.
I just wanted to know, like, if we are doing a self-learning. I was asking if we are doing self-learning on this, how long does it take to like self-learn a software? Like,
Yes, Akshita, when you started learning AutoCAD or SketchUp or any other software, how much time did it took you?
it's a process, yes, of course. It's not like we learn it in a day or two. But then for advanced softwares like Grasshopper and all, which are like new and we are not very used to it, so we are just getting into that.
So as a beginner, I would say that you just have to start, as you yourself mentioned that it is a process. So every software has its own process. It is based on an individual, how fast he or she can grasp it. So when I started learning it was a process. It was a big process. I took like few months. I don't remember how many months I took, but it's definitely a process, as you yourself mentioned. So I can't give you like an estimated time, like say, I can't tell you within 6 months. So what you will have as a mindset is, oh, within 6 months I can learn this software. But it is not that. It is based on how much you're interested in, or how fast can you grasp it, or how fast can you learn that software. It is all based on an individual. So there is no like a time limit or anything. Yeah, does that help answering your question?
Yes, sir. And also, is it like very self-learnable, or
Yes,
how did you
definitely.
do it?
So in today's world, anything and everything can be learned by YouTube. Anything and everything, I would say anything. So whatever, like say you can learn machine learning by YouTube. You can learn coding, the basic coding language like Java or C++ or whatever it is. You can learn by YouTube. You don't have to attend any classes. So when I was say, I'll just give an example. When I was learning Revit, I started learning from YouTube itself. I did not go to any classes or anything. So with the help of YouTube itself, I learned that software. So from YouTube, you can learn anything and everything. Each command, each iteration, each space, or each way how Rhino or Grasshopper works, it can help you with. It is just that your personal method of how you adapt to learn that software. It is like that. Yeah.
Okay, sir. Thank you.
Yes. Sure.
Any more questions?
Just again on behalf of students, one more question. I'm sorry,
Sure,
keep
sure.
talking. Yeah.
No,
Is
it's
it,
all.
yeah. Now, is it utterly necessary, or is it mandatory necessary to know coding if you have to do computational design?
No, no. So as in the presentation, I have mentioned like computational design is not equal to coding. So you don't have to learn coding at all. It is your personal choice if you want to learn. That is different. So if you learn Rhino and if you learn Grasshopper, which is not a coding language, it is just playing with repetitive space where you're trying to put in inputs to the design and how it's going to form up. And once that form is done, you just have to use like the locally available material. Like you can do a DIY, do it yourself. So that as you saw in the Cornell University's studio, where the students are using just hand-picked material and they're trying to show the design to the juror, so the juror can understand what the design process is or what they're trying to achieve. So with these softwares, what is happening is in real time, people are just as in a lot of designers, a lot of architects in different other countries. What they are doing is they are just using these softwares and they're just trying to make an installation. So once that installation is done, they are just putting it in an exhibition, or for people who wants to come just hang out there, who want to view that installation, who wants to take photographs. So everything and anything has become social media these days. So these installations, which are iterated, which are generated by Rhino and Grasshoppers, are done and then put it on the real world, and then those installation becomes like a landmark in that particular talk of the town. It becomes a talk of town. So all these, this advanced Rhino and Grasshopper software is mainly for mainly to iterate your design and mainly to come up with multiple options you want to produce, you want to showcase it. So that is really interesting, I would say.
Okay. Thanks. Thank you.
Sure, sir.
Any more
Any more
questions
questions?
from the students' side?
Hi, Dikshit.
Ashit,
Thanks for the interesting session. I hope all are
definitely,
done
ma'am.
with the question. It was a very enlightening session. I think there is a question from.
From Harshit.
Yeah. Okay.
Yeah. What is your question, Mr. Harshit?
Okay, thank you, Dikshit. It was a really interesting presentation, especially for giving us a very clear and broad understanding about computational design and also various
Definitely,
softwares which are associated with it. On
definitely,
behalf
definitely.
of all the faculties and students of Hindustan University School of Planning, Design and Architecture, I extend my hearty thanks.
Thank you, ma'am. Thank you so much for the opportunity.
Thank you, Dikshit.
Thank you so much for coming, Dikshit. Is
Thank
Devishri
you.
ma'am
Yeah,
here?
Devishri
sure.
ma'am.
Oh, okay. Sorry. Hi, ma'am. Thank you. Thank you for your kind words.
It's so nice also to see you presenting. And how was your experience? How different was it from here?
Definitely, totally different experience and exposure. I would say in every aspect, like learning wise or presenting wise, or how we are going to present it in the real world, work wise. Everywhere, in every platform, it is totally different. You cannot have any comparison between here and abroad. It is here. It is a different way of learning. In abroad, it is obviously a different method of learning. So everywhere you're going, you're just learning, but you're just trying to adapt wherever you are. So it is definitely an interesting one, I would say.
Okay. Okay, good.
Thank you, ma'am.
Thank you, Dikshit. That was a very lively presentation with a lot of videos and GIFs you have added. It was very interesting for the spectators, for us to see the webinar as well. And thank you for sharing your knowledge on the computational design to the students, because that is the future of architecture. We are all moving into the next level of architecture. I'm sure the
Yes.
students would have been benefited out of it, and I'm sure they'll be coming up with even more doubts and ideas hereafter to go on. So please, in
Yes.
future, if you can join us in the college after the reopening and all, to help our students in more of the software knowledge.
Sure, I'll do that. I'm willing to do that. I would love to do that. Definitely.
Thank you. Thank you.
Sure. Okay. Take care.
Okay, thank you. Thank you. Thank you everyone for participating.
Thank you, everyone. Yeah. Bye bye.
Bye.